Okay, so in this talk, my so my focus will be about this categorical trace. Yeah. Okay. So first, let me make a brief recap about what we want to achieve. Okay. So we consider this group pair G and H, where G is GLN cross GLN minus 1, and H is GLN minus 1, embedded in the most canonical way. And we fix a geometric so we fix the local system sigma, which is a product of two local systems, sigma n and sigma n minus 1, which are geometrically irreducible. Geometrically irreducible local systems. On the curve C. And we want to consider this modular space of Shtukas. That means we need to fix some co-weights for the groups G and H. So we choose some specific kinds of co-weights. It's these those co-weights corresponding to the standard representation or standard dual. So for each sequence of signs, you can so you have the sequence of co-weights, which are some co-weights of H, and also regarded as co-weights of G. Say, for example, if I want to explain the meaning of this notation, I tell you what is mu, 1 minus 1. So it means these two co-weights, 1, 0, 0, and 0, 0, minus 1. Okay. Hope this explains the notation. And for each kind of this trace, so I consider this modular space of Shtukas for H, with multiplication type determined by this sequence of co-weights, and I can also fix the degree of the vector bundle here. So you have this modular space should HD, and it maps to this should G D, and let me call this map by pi Shtuka. So, and of course, so here D is any with an integer, and it's indexing the. I think I turned it on. Is it? Yeah, I think it's turned on. Yeah. Okay. Okay. Thank you. Yeah. Then I define the special cycles to be the push forward of the fundamental class of should H. Yeah. Okay, so for this fundamental class to be defined, I'm using the should H is I'm using the should H is smooth, and for this push forward to be defined, I'm using that this map is finite. And that's something true for this Shtuka modular spaces, and it's a Borel-Moore homology class. So that's equivalent to say it's a dual vector in the compactly supported cohomology of Shtukas. Okay, so it's some dual vector here, and so recall that I want to study its restriction to some sigma isotypic part. So it's by definition this element, but you restrict to the sigma isotypic part of the compactly supported cohomology of Shtukas. you have the sigma isotopy part, and it's defined using this Hecke algebra action here, and this sigma isotopy part is something very explicit given geometry Langlands. So say for example, it's just a zero vector space. If the sum of the signs is non-zero, that's because in this case, this Shtukas moduli space is empty, and it's the cohomology of the local system, but some tensor power of it if the sum of the signs is zero. Okay, so yeah, so your job is to try to understand some elements in this very explicit vector spaces, and also you have this this intersection pairing, which is a bilinear form on the middle dimension compactly supported cohomology of Shtukas. So I only care about is on the degree 0 component. It's the bilinear form in this sense. Yeah, so I think mostly parallel to these special cycles. So you also care about its restriction to the sigma isotopy part, which is this thing, and okay, so you restrict it to the sigma isotopy part and tensor with the sigma star isotopy part. So yeah. Yeah, so as I have said, so I think our goal is to understand these two things. Understand this V d mu sigma and this this intersection pairing using categorical trace. Okay, so I think that's what I'm going to do in this lecture. Yeah. Okay. So okay, so now I can start to say something about the categorical trace. Okay, so what's the setup? So you should have a category and some endofunctor of the category, and so strictly speaking, you are working with some object inside this category, so-called PRL, and here I restricted my attention to those categories that are linear over QL bar. So it's not very crucial for our purpose to rigorously define this thing, but its object. So you can think of just conceits some categories linear over QL bar. Of course, here by categories I mean presentable infinity categories and linear over QL bar. And its morphisms are more interesting. So they consist of functors that functors preserving colimit. Okay, so yeah, so that's this category. PRL is an infinity 2 category, and so suppose you have a category and an endofunctor here, then there's a notion of categorical trace. So I write it as trace of F on this category C. So it will be a vector space. And how is it defined? So, sorry, I forgot to mention that. Okay, so I need to require this C to be dualizable. So what does it mean for C to be dualizable? It means that you can find another category C du such that there are two maps. One is the unit map. So from the category of vector spaces over QL bar to C tensor C du, and it's called the unit of C. And you also have a map from C tensor C du to the category of vector spaces. So it's called the co-unit of C. For C to be dualizable, it means that so you have this category and these two maps and satisfying some compatibilities. That's the meaning of dualizable category. And now this tensor product may seems to be a little bit abstract for you, but later when we go to examples, you will see how this tensor product works. So to define categorical trace, so you see that there's an obvious map from this to this, which is given by F tensor with identity. And the categorical trace is defined to be this composition. Since all category, so this function will be given by tensor with some vector space where the vector space is our categorical trace. So this is the definition of categorical trace, but it's okay. So if you haven't seen this before, you can think of that C is a vector space, and this C du is really the du vector space, and you can try to see that why this gives you the notion, your notion of trace of endomorphism on a vector space. And you will see that for a vector space to be dualizable, it really means the vector space is finite dimensional. So let me call this diagram star. Okay, so then I'm going to give an example, but I'm not going to give a trivial example, but it's most non-trivial example we are going to use. So we take this C to be the category of sheaves on Wang G. Okay, so it's the main focus of geometry Langlands, and you may have and you also want to put this nilpotent singular support condition. So I think the idea is that the entire category of sheaves on Wang G is too large, and you put some singular support condition to make this category smaller. Okay, so suppose you take C to be this category, and this category will carry two kinds of endomorphism. So the first kind is given by the Frobenius. So for example, you can push forward using the Frobenius. Okay, so this one kind of endomorphism. And another kind is given by this Hecke operator. So I will denote it by TV, where V is a representation of the dual group. Okay, so suppose you consider this, then I think it's a great theorem in geometry Langlands says that so the categorical trace is something you are. So if something you are familiar with, it's a space of automorphic functions. It's the compactly supported functions on GFQ. Okay, and this is the main result of Rankin, Gaisgray, Kashdan, Ruskin, Rosenblum, and Warshawski. Yeah, so that's the categorical trace. And there's also a variant which is more important for us. So, so for example, you can consider the endomorphism, which is the composition of Frobenius and Hecke operators. And you consider this categorical trace. Then I think it's proved in the same series of papers that this is the same as the compactly supported homology of Shtukas. Okay, so I probably haven't introduced this. Maybe let me put a view here. Okay, yes. So, okay. Since this is very crucial to our application, so I will. So I want to briefly summarize how these two isomorphisms are proved. So yeah, so how it works. Okay, so suppose you want to prove the. Okay, so suppose you want to calculate the categorical trace of this category. Then what you need to know is this dual category and this tensor product. So, and you also want to know the unit map and the co-unit map. So yeah, so try to compute this tensor product. Oh yeah, so the first thing you need to figure out is that many categories you will encounter in geometry are self-dual. So say, for example, in this specific case, the dual of Shif-Liu of Wang is itself. Yeah. So what you really want to construct is the map from vect to this and the map from this to vect. And then the next thing you need to do is, since this tensor product is very abstract, you want to make it something concrete. But there's an obvious candidate for this kind of tensor product, which is the Shif-Liu on Wang times Wang. And there's an obvious functor between them, which is given by the exterior tensor. And I think one of the main results of AGKRV says that this is the equivalence. And this theorem is actually highly non-trivial because if you remove this nilpotent single support condition, then this is not true, and it's far from being true. But yeah, so this equivalence really heavily relies on the geometry of nilpotent cone. So yeah, so you have this thing. Then you want to describe the unit and co-unit. Now you just need to describe one object here and one functor out of it. And there's an obvious candidate for a functor out of it, which is, okay, so you can pull back along diagonal and take compactly supported cohomology. Okay. And so what about the unit? So since here I'm using upper star and lower Shtukas, so to have some good base chain property, you also want to use upper star and lower Shtukas here. So a natural thing to put is this diagonal lower Shtukas of the constant sheaf on Wang. Okay, but this sheaf doesn't have nilpotent singular support, so you need to modify this by the so-called Benison spectral projector. So it's this functor iota r, and what is it? It's easy to define, but to study it, it's you really need to do something non-trivial. Okay, so there's a fully faithful embedding from the Shif-Liu of Wang to sheaf of Wang. And this function is called uta. And this is right and right. Okay. Yeah. Yeah, so that's this function. Yeah. So then you see what do you need to compute the categorical trace. Okay, so now you want to use the diagram star to compute the trace. Then how do you do it? So okay, so you have a map from vect to sheaf loop of Wang times Wang. And a functor and the endo functor here. So sheaves on Wang times Wang. And to vect, where this functor is given by delta upper star and can by support homology. Yeah, for this, so priorly you want to apply the spectral projector uta r to this diagonal shrink of constant sheaf. Well, however, okay, so it's a main theorem proved in AJKRV says that you can actually drop the nilpotent single support condition everywhere, and so since you drop that condition, then you don't need to apply this spectral projector to this object. And here, yeah, for the purpose of computing trace, and that's really something non-trivial that is proved in the paper HKRV. Yeah, and okay, and there's okay. So suppose you want to compute the trace of Frobenius, right? Then this functor is Frobenius times identity and shrink. Okay, and so if you want to compute the categorical trace, you see that. Okay, so here the functor I'm using are just upper star and lower shrink. They will satisfy very good base change properties. So it's really a formal computation given this, that this is a tensor product with compactly supported functions and function FQ. Well, so you may worry how function appears, but I can just write it as compactly supported homology here. Yeah, so that's how you compute this categorical trace. Yeah. Right. So that gives a categorical trace interpretation of the compactly supported homology of Shtukas. But now our job is to understand some homology class. So that means you want to consider a map between vector spaces. But suppose both vector spaces are realized as categorical trace. Okay. Say, for example, you want to study a map between vector spaces, where the first vector space is really the categorical trace of a category with an endo functor. And the second is it's also something like that, D to DG. And so how do you construct a map between them? Then you just need to construct a functor between these two endo functors, and that really means a commutative diagram, like this. So suppose you have a functor L here, together with a natural transformation eta. Okay, and then you may try to produce a trace of eta that gives you a map between these two categorical traces. Then you can try to see how this can work. Okay, so what is categorical trace there? It's really this diagram, vect to C tensor C do, and to C tensor C do, and to vect. Okay, and the second is similar diagram. Tensor D do to vect. Okay. Then the composition of the upper row is a trace of FC, and the lower row is this trace of GD. Then you see that to construct such a thing is equivalent to construct a natural transformation for this entire square. Yeah, that data is a natural transformation in this direction. But you see that this square can be cut into 3 squares. So you really need to construct 3 natural transformations like the following. Okay, yes. Okay. Then the question arises is that what functor should you put here? So you see that on the first factor you can just put L, right? But on the second factor, there's no natural thing to put at the first glance, because if you take the dual functor of L, it will be from D dual to C dual. Well, yeah, so that means, okay, so this condition is not enough. So you really want this functor L to admit a right adjoint. Okay. So suppose this L admits a right adjoint. Okay, so here by right adjoint, I mean has a right adjoint in the category PRL. So that means the right adjoint preserves colimit. So given such a right adjoint, you can put the dual functor right adjoint here. It will be from C dual to D dual. Right, and you use the same functor here. And it's not hard to say to see that you have these natural transformations. So, yeah, this gives you such a map between categorical traces. And I think that's all I want to say about the abstract formalism of categorical trace. So, any questions so far? Oh. Yeah. Yeah, that's true. But here I'm using that the PRL is symmetric monoid. Yeah. Right. Okay. So now I'm going to apply this formalism to this specific setup. So I want to draw a diagram. I don't know how to call it, but let me just give it a random name. The fundamental diagram, in the sense that it's fundamental in this work, not in the sense of it's fundamental in mathematics. Oh, you mean the natural transformations here? Yeah. So for this natural transformation, it's just this square. Here you put F tensor ID and G tensor ID here. Well, and for these two natural transformations, it's almost tautological from the definition of dual functor and right adjoint. Yeah, And I think later you can see some diagram of this shape, but with C and C do explicit, and I hope that explains better the situation. Thanks for asking. And oh, fundamental. Okay, so yeah. So recall that what I'm trying to understand is so it's really a map out of this compactly supported cohomology of Shtukas. Well, of course, you put some shift here since it's so you have a map from it to QR bar, which is given by the special cycle. And you want to restrict it to the sigma isotypic part. Yeah. But I have already this compactly supported cohomology of Shtukas can be realized as a categorical trace. It's really the trace of this category sheaf Liu Bang G. Okay, and the functor you should put here is this Frobenius composed with Hecke. Okay, now it's a composition of Hecke operators. It's Hecke associated to this sequence of co-weights. It's just a composition of Euro Hecke operators, and for some not important reason, I will put a shift here. Yeah, so if you take trace of this, you will recover this vector space. Then suppose you want to understand this functional, you want to produce a category here whose categorical trace is QR bar. Then there's the obvious choice, which is the category of vector spaces. And the functor, you can use the easy functor, which is the identity map. Okay, so the trace of this is QR bar. And now you want to restrict it to the sigma isotypic part. But the sigma isotypic part is also something very explicit. It's just the cohomology of the local system that tensor to some power. Well, so I think from now on, I will assume this Shtukas modular space are non-empty since the empty case is not interesting. Okay, and I put some shift here, not so important. Yeah, so the map from isotypic part to this can be really identified as a map between vector spaces like this. And you also want a category whose trace is that, but you also have a stupid choice, so you can use a category vect. And the functor you put is just tensoring with that vector space. Yeah, okay. So to understand these two maps, you only need to understand two functors. Like this. And you want to construct some natural transformations such that it traces these two maps. And now let's first see what kind of functors should you put here. Okay, so here you want some functors which produces this sigma isotypic thing. So there will be, I think there will be a very natural choice, which given by just tensoring with the high eigensheaf. Okay, so these are the functors. Yeah, and well, now you need some functors to encode this special cycle, and this special cycle is really something attached to a period. So you need to put the functor that is related to period. Then there's a very natural candidate. It's given by the this period integral operation that that has been talked about in many talks. Okay, so let me call natural transformations 1 and 2. So I have not given you the definition of 1 and 2, but let's first try to see what conditions do you want 1 and 2 to satisfy. Okay, so yeah, so you want, suppose you take the trace of 1, that gives you a map from this to this. So you want it to produce the sigma isotypic part. That means you want, suppose you, oh, sorry. I put a D here, so let me also put a D here. Okay. Yeah, so you want the image of trace 1 to combine combine all the degrees. So you want the image to be equal to the sigma isotypic part. Okay, so that's the first requirement. And the second requirement is that you want the trace of 2 to be equal to a special cycle. Okay, yes. That's all conditions you need for this natural transformations to satisfy. Oh, and here I should say something about these two functors. Okay, so here you see that for this map between categorical traces to exist, you really need this functor to have a continuous right adjoint. That means you have a right adjoint preserving co-limit. So this is true for this functor, but it already uses some hard result of geometry Langlands saying that the functor from sheaf noob to sheaf preserving compact object. But anyway, it's true for this functor. But it's not true for this functor, but that's just for stupid reason, because so you are considering a non-semi-simple group GLN, and GLN has a center, and that makes this Hecke eigensheaf not a compact object here. But you see, it's just the issue of center, and there's some tricks to overcome this difficulty. So I think in my talk I will just pretend these two functors preserve compact objects and do the operations. Okay. So so I think given this, let's try to see what does it tell you about the isotypic part of special cycle. That means you look at the outer square of this diagram, because eventually you just want to study the composition of these two. Okay, so the sigma isotypic part of the special cycle should be a functor of this form. Should be a map between vector spaces of this form. Okay, and given these two conditions, you will see that this is the same as the trace of the natural transformation 2 composed with 1. So that means if you want to understand this, you just need to understand the composition of the two natural transformations there. So you only need to understand a diagram like this. But now you see that the categories here are very, very easy, just vector spaces. And the functors are also not very hard. It's tensor with this vector space with the isotypic part, and these two functors are just given by something you have already seen in the first talk. Okay, just given by tensor with this thing. And here is duality. What's not obvious here is really this composition of natural transformations. Right. Yeah. It's not home space, strictly speaking. So you see that. So you have this duality on shift nupe of Wang G, and it has a co-unit map, and it's a co-unit map for the miraculous duality. So it's really so you put pure shift here and eigenshift here, and you pair them. Yeah. Yeah. Up to some miraculous duality. Exactly. Yeah. Thanks for the reminder. Okay, yeah, so now you see that what kind of thing you need to understand. So you just need to understand this natural transformation, right? So what is really this natural transformation? So it's just a map between vector spaces. So what's the composition of these two functors? It's just tensoring together these two vector spaces. And composition of this is just this. And what you need to understand is the map between them. That's this two composed with one. But so I haven't tell you the construction of 1 and 2, but you see that the functor in the middle in this fundamental diagram is the composition of Frobenius and something purely geometric, which happens over FQ bar. So you can. So after I give you the definition of 1 and 2, you'll see that it's. So this natural transformation naturally is split into two steps, where one step only involves the Frobenius. So it's just given by the Frobenius endomorphism on this vector space. And another step happens over FQ bar. So it's here will be something mysterious at the moment, the so-called A epsilon. And okay, so you want to understand this, then you just need to understand what is this A epsilon, because I assume that you understand this Frobenius. Okay, so you only need to study this A epsilon on the right. Okay, so suppose you understand this. How do you compute this? So it's given by something very explicit. So suppose you have some element m here, then where it gets mapped to. So it's just a trace of A epsilon m. So what's the meaning of A epsilon m? So regard it as an action of this vector space on this vector space, then A epsilon m is some endomorphism on this vector space, and you can compose this Frobenius on this vector space. Okay, so that's this map. So it's just the only reasonable way to take trace of this composition. Okay, so yeah, and okay. Then let me just say a word about the intersection pairing. So you can study the intersection pairing restricted to the sigma isotypic part in a similar way. Yeah. So I think you can imagine you just need to replace this functor by something else. That's okay. So now I'm going to define these two natural transformations. So, any questions so far? Yeah, exactly. So I think in the next talk we will see that. So this A epsilon, if you combine all epsilon together, it just gives you the Clifford algebra action on the pure integral of eigenshift. Yeah, exactly. Okay, so now let me first explain what is one. Okay, so one is easy, and I think you can already see such a natural transformation from the definition. So it just uses the Hecke eigenproperty and the Frobenius structure on the Hecke eigensheaf. So, what's the data of one? So you want to construct a natural transformation in the following form. So you want to map from this. Okay, so that's this composition. And that composition is Frobenius Schrick composed with Hecke on this Hecke eigensheaf. Well, but you know, this is Hecke eigen. That really means that this is equal to, this is isomorphic to the Hecke operator and applied to the Hecke eigensheaf. That just comes from the Hecke eigenproperty. And you see that there's an obvious map here. It's given by the Frobenius. It's because everything is defined over FQ actually. So there's such a map. Okay. Yeah. So that's the natural transformation one. Oh, and I should say that. So why you have such a map? Because Frobenius lower Schrick is the same as lower star. So okay. So that's one, and you want one to satisfy the image of a product of trace one to be equal to the sigma isotypic part, but it's mostly formal from the construction. Okay, it's not mostly formal; it's just formal. It's formal from construction that this image will lies in the sigma isotypic part, because you can imagine just, okay, from the Hecke eigenproperty of this, you can deduce the Hecke eigenproperty for its trace, right? So this is formal. So the only thing you need to show is that, okay, so you only need trace one is injective. Trace one is injective. Right, but I think there should be many ways to see this. Say, for example, from the spectral side. But so the way I see this is that, okay, so you can study the intersection pairing and show that if you pull back along this map the intersection pairing, then it's non-degenerate. And that's what I'm going to talk about in the next talk. So it will be, okay. Yeah. So yeah, so that's one way to see the injectivity. Okay, so now let's come to the more interesting natural transformation two, since it's related to the pure interval. So okay, so to explain two, let me first recall you what this two is. So you have a map from bound H to bound G, and you have the pure sheaf Px, which is the lower Schrick, the constant sheaf on bound H, and right, and okay. So what's this integration along X? I think it's just like okay, so it's really okay, it's like you first tensor with this pure sheaf and take compactly supported cohomology. So it's a function out of sheaf nu plus Wang G, but actually it's defined on the entire category sheaf Wang G. Yeah. So that's this functor. And okay, now I need to switch to another board. Sorry. And so what's the data of such a natural transformation? So it's really just you first write down the two functors. So the first functor is so you have this Frobenius and Hecke, and with a shift applied to something, and then tensor with pure sheaf and take compatible cohomology. This is this composition, and this composition is just take compactly supported cohomology, and you first tensor with the pure sheaf. So you want such a natural transformation. Yeah, so this is the data of 2. Well, but you see that this thing you can simplify it a little bit using projection formula. So it's just compactly supported cohomology of something with, so you remove this lower shrink to upper star. Yes, upper star px. And the Hecke operator will be, it's some satisfying some self-adjoint property, but you need to put a dual here. Okay, so this is just this. Yeah, so you need a natural transformation in this direction. That means you just need a map from this dual Hecke operator, composed with Frobenius, applied to the pure sheaf, to pure sheaf itself. Right, that's all you want to construct. But you see that there's an obvious first step you can do is to drop this Frobenius. So it maps to TV star pure sheaf. And then what you really need to construct is such a map. And I will call this map. And I'm going to construct this map, and I will call it math frac C in frac C ipsilon. And so I somehow call this the Frobenius twist. Okay. Yeah. And yes. Oh. Okay. And what really is this kind of data C? So I want to say that it's really the data of a cohomological correspondence. Okay. Okay. So actually, I can directly tell you the definition of C, but I think it's maybe worthwhile to say a little bit about the general formalism of cohomological correspondence. Okay. Yeah. So first, what do I mean by cohomological correspondence? So suppose you have a correspondence between two things. I think, say for example, for any pre-stacks. You have a correspondence between them, and you have a sheaf here, and then the space of cohomological correspondence supported on C on the sheaf F correspondence from F to F is defined as a Helm space from Okay. So given a correspondence, you can apply it to F, which means you start. So you do upper star on one map and lower streak on another, and then you home from the resulting shift from itself to itself. Yes. Oh. Okay. You mean here you need to put a kernel, right? Yeah. So in this picture, they live on A. I think I will very soon. In this case, it's Bang G. I will write it very soon. Yeah. Yeah, but you can further push forward along the curve. I mean, you get something about it. Yeah. That's what I mean by Hecke operator. Yeah, exactly. Yeah. Okay. So this is the data of cohomological correspondence. Okay, and of course you can write using some obvious adjunction. Oh, and of course, I mean, so whenever I write this lower shriek and upper shriek, I'm assuming it's defined. So you need to assume some. Yes. Oh, I will write. Okay, so I will write it right now. So what I see is this Hecke stack. Oh yeah, exactly. Yeah. Sorry, but C is for correspondence. Yeah, sorry. Right. Yeah, A is a spongy. Right, and the two maps are given by Hecke left and Hecke right. Yeah. So this is the situation we want to consider, and you see that. Okay, so it's just follows from my definition is that. So this home space is really just okay. So I'm doing nothing but just change notation. Homological correspondence on Hecke with respect to Px and P. Okay, of course up to some shift that I ignore at the moment. Okay, so yes, so what's the advantage of introducing this notation? So okay, so I want to say that there are some ways, there are some natural ways to construct a cohomological correspondence. So suppose you have a correspondence in which this map is smooth. This left map is smooth. Yeah. So in this case, you see what's this cohomological correspondence? Say, for example, between this constant shift on A. Well, it's the same as home from, well, you see it's QL bar upper star to QL bar upper shriek. Well, but since you assume that C left is smooth, you can replace this upper shriek by upper star. So it's the same as home from QL bar to QL bar shift by something. Shift by 2 times dimension of this map. And then you see that there's an obvious thing here. It's given by identity, but it lives in some cohomological degree. And this thing is called the fundamental class. It's the so it's a relative fundamental class of C over A. Okay. Okay, yeah, so this gives you some kind of construction of cohomological correspondence on the constant sheaf given smoothness of one map. Well, but what you actually need is a cohomological correspondence on the pure sheaf. And for that purpose, I want to write. And the pure sheaf is a push forward of the constant sheaf. So I want to say that there's a push forward functoriality of cohomological correspondence. So the setup is the following. So suppose you have two correspondences, C on A and D on B, and two maps. Well, map pi, C right and D right. And you have a map between the correspondence space pi Hecke. And suppose F lies in sheaf A. Well, then what you, yes. Oh, what's this map? Oh, it's some other map. It's not so important. Oh, because because constant sheaf pull back to constant sheaf. Yeah. So, yeah. Oh, yeah, sorry. Yeah, sorry. Thank you. Okay, so, yeah. Okay, so what's this push forward map? It's really, so you want to map from the cohomological correspondence on F to a cohomological correspondence on pi lower Schrick F. Well, of course, I'm assuming pi is Schrickable or something. Okay, so I still want to call this map lower Schrick, but it's not, okay, but this operation is not universally defined. It's only defined when this diagram is so-called pushable. So suppose it's pushable. That means, so if you form a fiber product here, then you have a map A, and this map A is proper, i.e. A is proper. So suppose you are in this case, I think you can, then you can just play with 6 functors. You will see that there's a base chain map from upper star. Oh, sorry. Yeah, right. Lower Schrick, upper star to upper star, lower Schrick. Well, so if you're assuming this pushable condition, I mean A is proper, there's such a map, and it's purely something from 6 functor formalism and not very interesting, and I'm not going to the detail of it. And from this, you can construct such a map. So I guess maybe let me say a few words about how you construct it. Okay, it's the home from C left Schrick upper star F to F, and you first apply pi lower Schrick to both sides. And then using this map, you will see that there's a natural map here. So it's some kind of construction of a new cohomological correspondence from old one. Okay, so I'm not going to use this diagram. Use this one. Okay, so so in our case, so the corresponding diagram will be the following. So so recall that so special cycles are really you're considering a map from Shtukas of H to Shtukas of G, but Shtukas comes from this Hecke correspondence. So you can actually consider the more primitive thing. So it's the Hecke of G and Hecke of H. So there will be a map from Hecke of H to Hecke of G, and it enjoys two maps to Wang G. Hecke of H enjoys two maps to Wang H. Yes, okay. So this is the diagram there. And how I'm going to define this C epsilon, I'm going to combine this and this. So it's really just, so, okay, so this map is called pi Hecke. And you can take, okay. Okay. Then you can push forward the fundamental class of Hecke H. Okay, so yeah, this should finish the definition of C epsilon underline. Yes, okay. And recall that what we need to show is that, okay, and we still need to show that the trace of 2 is the same as this special cycle, and 2 is constructed from this cohomological correspondence. Okay. Okay. Oh, yes, I forgot to mention that. Okay, so these two maps are proper. So in particular, if you form fiber product, this will be proper. And this map is smooth, so you have fundamental class. So this makes sense. Thanks. Oh God, this one. Okay. Oh, I need to hurry a little bit. So, okay. So we need to do this. So for this purpose, I need to introduce this so-called sheaf cycle correspondence. And I think it's sometimes called the map of local terms. Okay, so what's the setup? Okay, so you see that what really is this procedure? So you are starting from some cohomological correspondence here to some fundamental class on this, to some push forward fundamental class on Shtukas. So these two constructions seems to be related because it's very similar. So for general correspondence, you can really consider this general setup. So suppose you have a correspondence between A and A and two maps C left, C right, and A diagonal to A times A, and you have this fixed point locus. Okay, then suppose you have a sheaf on A, but you assume it's constructible. So by putting C here, I mean it's constructible. Then there will be a map called sheaf cycle correspondence or local term. It's you starting from a cohomological correspondence on F to a Borel-Moore cohomology class and the fixed point of the correspondence. Well, by Borel-Moore homology, I mean it's due to compactly supported. Right. So how do you construct such a thing? So it's given by the following procedure. So I think I'm not giving you the most standard way of making this construction, but I will present it in a way that is quite close to some categorical trace. Okay, so you consider this diagram. To that. Okay, and you put diagonal Shurui constant and diagonal pullback and compare the supported cohomology. And here you put the functor induced by this correspondence. Well, and why I write this diagram? Because the composition will be the compact support cohomology of the fixed point locus. Well, that just follows from base change things. And you want to construct a functional out of it. You want to construct a map from it to QL bar. Then you just put some vect here. Vect. And you put identity everywhere here. To construct such a map, you just need to construct natural transformation as before, and you just need to construct the 3 natural transformations here. Okay, yeah. And you need to think about what functor to put here. Well, unfortunately, okay, so you have a diagram here, actually. Okay, let's see. Okay, so what functor to put? So so the correct functor is you first tensor with a sheaf F and exterior tensor with a Verdier dual of F. And since I need this Verdier dual, that's why I require F to be constructible. And yeah. Yes. So here you use the same functor, and it's not hard to see that you have these three natural transformations. Yeah. So say for example, this natural transformation will just follow from the data of a cohomological correspondence, and this will just follow from the standard 6 functor formalism, something formal. Yeah. So this explains this construction. Okay, so well, oops. Right? It's very tricky. Okay, so I need to. Okay, now let's back to our setting. Now in our setting, the correspondence we want to consider is really this high correspondence. So you have this high stack degree D, and it maps to Wang G D times Wang G D. Well, here I'm assuming Shtukas space is non-empty, so it's really correspondence between D and D. And you form this fixed point locus, but you twist once the high correspondence map. Then the fixed point locus is really Shtukas. Okay, so this sheaf cycle correspondence really gives you, so recall that you have the cohomological correspondence, which is the following data. Page left, shrink to the pure sheaf itself, to some shift. You have a cohomological correspondence called C epsilon, but you make a Frobenius twist. And then this will gives you a trace of, so I forgot to name this as, I also want to name it as trace. Okay, this gives you a trace of this cohomological correspondence. But now you see that it doesn't involve any kind of categorical trace, because although I write categories here, it's just some construction on object. I mean, the entire category doesn't play a role. So it's some element here. Oh, and if you keep track of the shift, you will see it's also middle dimensional here. Then recall that our job is to show that the trace of 2 is a natural transformation between category, and this is really a map between categorical traces. So you want to compare it with the special cycle class. Well, then this thing will serve as a bridge. So really prove this equals to this by first proving this identity and this identity. So I claim that this identity will be formal. I think it's not very hard to believe, because if you remember the diagram involving categorical traces, it's very similar to this one, modulo the difference between the nuke and without nuke there. And I should say that, okay, so the theorem of AJK-RV is really hard and relies deeply on the geometry of nuke, but this identity doesn't involve, it's just something formal. Okay, so this is formal, and this identity needs some explanation. And why you have this identity? So you take trace of this. Then what really this thing is. So recall that it's constructed via a push forward of another cohomological correspondence, which is given by a fundamental class. It's really a trace of push forward of fundamental class. And the first thing is that, so the trace and this push forward can be swapped. Well, but I have stated that this is not formal, unfortunately. This thing is formal if this map pi is proper. However, what is pi? Pi is the map from bang H to bang G. It's not proper, so it's not formal. But what we proved in the paper is that so it's okay in this case. So the main reason for this is because you have a Frobenius twist, and somehow uses the compactification of the map from bang H to bang G, and to go back to the proper case. So this is the first identity, and the second identity is that the trace can be swapped with the fundamental class. Okay, trace of fundamental class is fundamental class on the fixed point. Well, so fortunately, this is formal. Formal in some sense, but it's still not so easy to prove. I mean, even if pi is proper, you want to prove that these two things can swap. It's not something easy. So, but it's still a formal proof. Formal if bond H is smooth. Okay, so I should okay. Formal since bond H is smooth. Okay, so this is okay. So okay, since my time is now, that I will stop here.
All right, then. Thank you for this wonderful lecture. So does anybody, including Yanis, have further questions now? Wait for the microphone if you do. Yanis. Coming up.
Is there, so here you're using a lot the fact that that X is homogeneous and you have ban H to ban G.
Yeah, exactly.
Do you have a sense of when you have natural cohomological correspondences for the period shift?
I think if X is, I think if it's induction from a subgroup from a vector space, I mean, yeah, if it's of the form V times H to G, if X is of this form, I think there's a way to define to define a fundamental class for yeah, I think in this case there should be a natural candidate. Because these fundamental classes are not only defined when the space is smooth, they're also defined when it's quasi-smooth. And in this case, it's quasi-smooth, and you can define fundamental class and still push forward. But in that case, I don't know how to do this. Yeah.
And another related question is, your constructions are by nature cohomological, so you get the classes of the cycles in cohomology, but these classes came from some cycle.
Yeah, exactly.
Is there a motivic variant?
I don't know what's motivic variant. I think only thing I can see is that this. Yeah, right. You can really refine this construction to define some Chow cycles, but I don't know. Say, for example, if you take intersection of Chow cycles, it's the same as taking intersection of cohomology class. I don't know. The cycle thing gives you some new invariant. I don't know.
But you're using Frobenius traces and all of this machinery.
Yeah, this. Yeah, I mean, but there's some. Okay, so I think this thing definitely there's the underlying Chow cycle, but this construction may be not so clear. But I think you probably can also use some motivic sheaves to make this construction. I'm not very sure. I think it should be possible.
Can you advertise a little bit what's coming up in the third lecture? So if I didn't follow all your constructions today, can I follow the third lecture?
Yeah. Oh, okay. So what I will talk about in the third lecture is really is purely about this thing. It's about this map A epsilon here, and it will be related to the Clifford algebra stuff. Yeah, right, exactly. And
right. Anybody else? Perhaps? Okay, if not, let's thank Zeyu again.
Thank you.